the third? Second lecture.
There's a moment.
Yeah, you wish I were the third and final. Oh, the third and final lecture of mine. Yes, yes. I was like, counting is not my forte, but I was pretty sure I'm the second person. Yeah, well, yeah, no, I mean, there's something, right? There's machine learning or something. Yeah, I mean, so in the next 2 hours, I'm just kidding. This is actually, I think, going to be a sort of shorter and smoother story. What I'd like to do now is tell you about another platform which is emerging for studying quantum many-body physics, which is intimately connected and in fact was originally developed, I would say, for quantum computing. I know there are several of you from Oscar Painter's group who actually build these quantum circuits, sort of more in this quantum many-body side rather than on the quantum computing side. In the interest of full disclosure, I am an experimentalist, but I'm mostly a cold atom experimentalist. I don't do any fab work. All of these fab experiments are done in collaboration with Dave Schuster's group. So if I say something which is wrong or patently untrue, I trust that you will correct me, please. Okay? But gently. I'm a delegate here. Okay, so I wanted to start by taking a step back from the platform for just a moment and think about how materials order quite generically. Okay? So this is to say, imagine we've implemented the first two steps that we wanted for building materials, right? In the first lecture we said the first two things that we need is objects that behave as particles, that is to say they have some non-trivial dispersion relation, right? You can apply forces to them and it changes their momentum, it changes their velocity, okay? So that's requirement number one. And requirement number two, for the thing to be considered a material is that these particles have to interact with each other. So the question is, once we have those two ingredients, how do we order these objects into a material? Well, you could imagine if they didn't interact, just putting them in the places you wanted them one at a time, right? But we're more interested in ordered states where the order emerges from interactions between the particles. And so the question is, what sorts of mechanisms lead to this kind of ordering, okay? And some of these stories apply more to the quantum regime, some apply more to a classical regime. Some of them I give you a more quantum mechanical picture, some it's a more classical picture, but let's just think broadly about what can happen. Okay, so what happens mostly with electrons? Well, the game is I have some particles, okay, that would just bounce off of each other ad infinitum. But I couple them to some cold bath, okay? I bring the bath into contact with the system. And the idea is that this damping that I put into this model actually essentially comes from collisions of these particles that are moving quickly with bath degrees of freedom that are moving slowly, okay? And so the physical picture you should have in mind is that if I have two particles with similar energies colliding, well, which one ends up with more energy and which one ends up with less energy is less clear, right? But if I have one particle with a lot of energy collide with one particle with very little energy, it's quite likely that after the collision, the one that had a lot of energy is going to end up with less, and the one that had very little is going to end up with more, right? And this is why baths are good for cooling things, right? The point is, the degrees of freedom in the bath are cold, they're low energy, so that essentially this damping friction, right, is the idea that when this thing moves past the degrees of freedom of the table, it can give its energy to those degrees of freedom. If the degrees of freedom of the bath were moving rapidly enough that they're moving faster than these particles, well, mostly what you would do actually is the bath would heat up your system, give it more energy, okay? So this is a microscopic picture of what I showed you before, right? The bath takes the energy out of this system and cools it down to some many-body ground state, Okay? So I would say this is how one can understand thermalization with the reservoir, and all of these ideas of many-body localization that you've been hearing about from Dima and Norm are really about this question of, to what extent can I make this statement? Well, when I couple a hot system to a cold system, the energy, we're going to explore all microstates at the same energy with equal probability, which means that essentially energy will leave from one end. To what extent is that true? Okay? All right, so this is one possibility, and this is the way we typically see ordering in electronic systems. Although, as I point out down here, sometimes we see quantum-based transistors there. Okay? The second approach is the approach that's typically taken with cold atoms. So the picture here is that I start with some very low entropy gas without many correlations between the particles. Okay, so this is our Bose-Einstein condensate. And there was a Nobel Prize for figuring out how to make this. And the essential idea there was to use evaporation, like in my coffee, right? So the point is, the high energy particles leave, right? Particles collide, one goes to higher energy, one goes to lower energy. The one with higher energy can spill over the top of my trap. And that leaves the system with, on average, less energy per particle than I started with. And you just keep doing this and letting the particles collide, lowering your trap. And eventually you end up with a very low entropy starting state. Okay? And then we rely on the adiabatic theorem. And what we do is we turn this trap into a lattice, okay? Which, as Emmanuel explained on Monday, reduces the kinetic energy scale and increases the interaction energy scale between the particles. And they should crystallize into 1 particle per second, into a lattice. Now, why do they crystallize? Because the system started in the many-body ground state, and once I have this lattice on, the many-body ground state will be 1 particle per second. And so this adiabatic theorem says, as long as I change the Hamiltonian slowly, I will stay in the same eigenstate throughout the process, with caveats and so forth. But this is this many-body Landau-Zehner transition, again, that Dima was just talking about. So the picture you should have in your mind is something like this. I go from a fluid that more or less looks like particles behaving as waves to this more crystalline, solid-looking object with 1 particle per second. Okay, and so this is typically the recipe that's used with cold atoms across the board. This is how one makes a Mott insulator. You can imagine now starting with a Mott insulator and adiabatically turning on spin-spin interactions. And so what I'm drawing here is, as a function of, say, the strength of these, spin-spin interactions, the spectrum of eigenstates. So this is an energy axis, and these are all of the different eigenstates of the system. And the point is, for very weak spin-spin interactions, the lowest energy state has 1 particle per site here, and 2 particles per site here, and 3 particles per site there. Or equivalently, it's some spin degree of freedom. Let's see if this actually just works. Wouldn't that be nice? You know it's a bad time when you think that. Well, that looks like good news. And now when I adiabatically turn on these spin-spin interactions, at the end I get some magnetically ordered phase out on the other side. Okay? And so the statement here is the system was able to fluctuate from some disordered state into an ordered state by colliding with particles in the bath. Okay? And so we call these thermal fluctuations drove a phase transition from some disordered fluid of particles to a crystalline solid. Here, we were at 0 temperature. We were in the lowest energy state of the system, right? And in fact, it was quantum fluctuations. It was non-commuting terms in the Hamiltonian that took us from our spin-polarized initial state to this spin-full final state, or equivalently here from our superfluid to our Mott insulator. So this is what we call a quantum phase transition. And indeed, you can see these in electronic materials as well by changing magnetic fields, changing pressure, what have you. Okay? So, what did I tell you about yesterday for optical photons? Well, I told you actually a rather different story. So imagine I have this trap, and it starts with no particles in it. So we start in this state. Well, what I told you was, I can excite the system, and if I excite at some high energy, I put particles into excited states of this trap. If I excite at slightly lower energy, I put my particle into a slightly lower energy state. And if I excite into this lowest quantum state, I put a single particle into the lowest energy state of the trap. Okay? So, how do I make a many-body kind of ordered state here? Well, now I can ask, what happens if I try to inject a second particle? Right? If I inject that second particle at fairly high energy, well, the point is my particles are repelling each other. So now, when I put in this second high-energy photon, actually, I end up in a final state where the two particles have repelled each other and moved out of the trap. If I put in this second photon at slightly lower energy, I end up in this two-particle state that's slightly lower energy, and if I put in my second photon at this lowest energy eigenstate, I end up in this lowest energy crystalline state. Okay? And it looks rather trivial classically, but the interesting point here is that when I injected this second photon, I went from having one photon in the middle to having two photons outwards on the edges, right? So in some sense, there's some non-trivial ordering going on due to the collisions between the particles, and all I'm doing is sort of spectroscopically resolving these states, okay? And so I would say this is a quantum computing, quantum optics inspired way to make many-body states. The challenge is that you need to know an awful lot about your Hamiltonian for this to work, right? We need to know what states it is that we want to populate to inject at the right energies. Okay? Yes?
So in cold atoms and also in solid states, people think a lot about temperature. So would you say in this approach, you're more thinking about something like entropy or a level of how you can prepare states, or do you also think about temperature?
So I think there are several really nice answers to that. The first answer, and at least I think they're nice answers, you guys get to decide whether they're nice. But just know that in my heart, I've already validated myself. So when I think about ultra-cold atoms, I only think about entropy. I never think. Why is that? Well, basically, the adiabatic theorem says that I stay in the same eigenstate as I vary the Hamiltonian, right? Does it say that the temperature remains the same? You can think of a very simple example of this. And in fact, if you all take nothing else from this lecture, I think this slide is really the most important bit even before we start talking about circuits. So if I have some non-interacting particles in a harmonic trap, okay? And they're in some thermal state to start with. So I have some in the lowest state, I have some in the first excited state, some in the second, and so forth. Okay, so this is my thermal distribution. But I'm not in contact with the reservoir, as I typically am not with cold atoms, right? What happens as I slowly reduce the trapping potential? Who thinks they change eigenstates? If I would do it slowly. Nobody, right? They stay in the same eigenstate. So, doesn't that mean the temperature drops? Right? Because the characteristic energy scale went down. So I actually cooled my system just by reducing the trap. But did I get anything interesting out of that? In this case, not really. So what remained fixed was the entropy per particle here. Yeah? And so there are situations where this is beneficial. Have you heard of adiabatic demagnetization cooling? Right? One can play these games with electronic spins if you isolate them well enough from the environment and cool them down just by putting them in a big magnetic field, coupling them to a bath to get them to some low temperature, decoupling them from the bath, and then turning down your magnetic field, and that cools the spins. And the reason this is useful is as you turn that magnetic field down, the energy in these spins reduces, the temperature of the spins reduces. And now you can use these cold spins as a new bath to make a material even colder. So fairly recently, I was unaware that there are microkelvin experiments going on with electronic materials, right? Like you don't have to laser cool to get to microkelvin temperatures. And the way you do it is with this adiabatic demagnetization technique, okay? But the point is that you better have something very particular in mind if you want to play this game with reducing the trap, because essentially, entropy is the thing that's conserved, and this temperature degree of freedom is not really such a sensible one to think about. Okay, so the first point is, here, I always talk about entropy per particle, and not the temperature per se. And then the next question here is, imagine I start in the manybody ground state here, and then adiabatically change my Hamiltonian. Oh, but I do it too quickly, so I put some non-adiabatic transitions in. Am I necessarily in a thermal state afterwards? Well, maybe Dina or Norm is a better person to ask that, but I would guess not. Do you know? Do the many-body shoot-throughs in the Landau-Zehner process produce a thermal distribution? Yeah. So in some sense, you have to be very careful then about talking about thermal distributions in any of these systems. And so then the state, but you can always talk about how much entropy there is per particle, right? And so similarly here, you ask the question, I meant to produce this state, but maybe I excited too quickly, or the lifetimes of the states were too short, so I accidentally populated several of them. And so you can ask about the entropy of the system, but I don't typically think about a temperature thing. And I think the other thing which is a little challenging in both of these systems is that we tend to lose particles, right? The thing that limits us if we wait too long, sometimes it's heating within the model, but sometimes it's particles just leaving. And that's much less common with electronic materials because there's this idea of charge neutrality. Things get very unhappy if you start to lose particles. And so there are a lot of processes that leave the manifold corresponding to the physical model that we want to study, and that's where the stuff gets here. Okay, so actually let's go back here for a moment. What I want to tell you about now is an approach for photons, which is sort of a hybrid of this spectroscopic approach, okay, and this thermalization approach. Oh boy, we get to go through this whole thing again, I apologize. We'll be up here soon. Okay. What we're going to do, ultimately, is come up with a way to have not just a thermal reservoir for photons, okay, but also a particle reservoir. Because that was the real challenge, right? We need a way to inject particles into our photonic system as they leak out. Okay, so there are all kinds of ideas about how one might do this, going back several decades. But there were both some understanding limitations to making this happen and some technical ones. And circuit QED is really what made it possible. So people had all of these different pictures of what a system of coupled cavities that microwave photons or optical photons might live in could look like, you know, to mimic this cold atom story. And so what I want to tell you about is how this has sort of been implemented in a couple of different groups around the world in this circuit platform, and how you should think about that platform, and then how we've implemented this, what I would call sort of chemical potential for life. So you'll see this throughout. The experimental work is done between my group, my last name is Simon, and Dave Schuster's group. His last name is Schuster. So what we're hoping is to get famous enough that the Simon and Schuster publishing house sue us. But just because we use their logo now. But I think we've got a ways.
This is recorded, John. You should be careful.
What? This is recorded? Well,
You have to raise that.
I don't want them to, please don't sue us. Deep into the camera. Okay. So,
How about a book on Simon and Schuster published by Simon and Schuster?
no, I mean, I think that would be a good compromise, right? Surprisingly, they have not yet asked us. Usually it's companies like that. Okay, so the first person who seriously thought about trying to do these kinds of experiments that I know of anyway is Andrew Howitt at Princeton. And he's got a bunch of really beautiful pioneering papers. The basic idea is to have arrays of superconducting resonators with qubits in them. And this is his artistic rendition. He may have actually had an artist make his. You can tell because it doesn't look like it was made in Mathematica. And so I want to tell you about how this works in practice. So we need lattice sites. Okay, for cold atoms, the lattice site is a laser potential, right? And the things that mimic electrons are atoms, right? And so you can ask how many atoms are there in the lattice site, and how strongly do they interact with each other? How much energy do we have to pay extra to put a second atom in compared to the first, okay? So what kind of an object acts like a lattice site for photons? Well, it turns out to be very simple, an LC resonator, okay? You can quantize an LC resonator. The excitations of that resonator are photons of energy, Planck's constant, times 1 over root LC, right? The resonant frequency. So this thing really just holds photons, okay? And the resonators I'm thinking of, if you want to deal with microwave photons, we say that this 1 over root LC is 2 pi times about 4.5 gigahertz. So, what is the interaction energy between the photons in a resonator that looks like this? Someone who's not an Oscar Painter's group. I can wait all day.
What was the question?
Pardon?
What was the question?
Okay, that's good. So now we know what is the interaction energy between photons in this LC resonator?
There's an error.
That's right. And so the way you can see this is the interaction energy is the amount of extra energy that I have to pay to put the second photon in, compared to the amount that I had to pay to put the first photon in. Right? This is this Hubbard view that Emmanuel talked about. Okay? So if I have an LC circuit, no matter how many photons I have in the circuit, the frequency of the circuit basically stays constant, right? Now, if I put enough power into the circuit, it starts to heat up. And once it starts to heat up, your inductor might deform, right? And then the frequency might start to shift. Yes? And we're all like, oh, that's silly. Well, one, that happens, and you have to be careful in high-power electronics. But two, essentially, that's the effect we're interested in, okay? Except we need to see it not for, watts of power, which is like 10 to the 18 photons in this circuit. We need to see it for 1 photon in the circuit. It shifts for the second one, okay? So the picture you should have in mind is to replace this inductor with what's called a Josephson junction, okay? For our purposes today, you should just think of this Josephson junction as an inductor whose inductance depends upon how much current is flowing through it. Okay? So, in practice, these are made by crossing 2 pieces of aluminum and leaving an aluminum oxide layer between them. Okay? We don't need to talk about why. We don't care about that. If you want to hear more about that, talk with anyone from Oscar Painter's group. But don't ask me about that part. Because I don't think carefully enough about it. I probably can't give you as good an answer as I can. Okay, but the point is this. If this inductance depends strongly on the current, we can have a situation where the first photon that goes in needs to be at 4.5 gigahertz, but then the second one might need to be at 4.2 gigahertz. Okay? So this corresponds to an attractive interaction of 300 megahertz, right? And these are sort of pretty typical numbers. Okay. Well, that's why I said it's an attractive edge. Well, as we'll see, in some sense, we're indifferent to whether it's attractive or repulsive. But yes, pictorially, through the rest of the talk, I'm going to pretend like it's a positive view, because that's what we're all used to thinking about, most of us anyway. But just know that it doesn't matter for any of the physics here today. Okay, so we've got this 300 megahertz of interaction. And these are actually the real numbers that people see in the experiments. And so in the interest of giving a broad introduction to this material, I thought I would point out that this is sort of the seminal theory paper. This is the first experimental demonstration of one of these objects. Okay, what you can see here is that this is an early Josephson Junction. Actually a Cooper pair box, which is a slightly different object, but similar. And what you can see here is that this meandering object is a resonator, okay? You should just think of it as a transmission line. The mirrors at the end, this object here is one of the transmission lines. This object is the outgoing transmission line for measuring. This squiggly thing is the mirror separating them. And they have one at each end, so that makes a microwave cavity, okay? And then you can couple your transmon qubit, which is this nonlinear object, to that cavity and do cavity quantum electrodynamics with that, just as one does with optical photons. The difference between doing this with optical photons and doing it with microwave photons, and I can say this because I'm an optical cavity QED person, is that circuit QED works much, much, much better. And I dropped about 5 muches there. So the point is, this is an early work from Dave Schuster and Rob Schulthoff and others, where they can, in a single shot, distinguish the number of photons in the cavity, okay, by the shift of the cavity resonance due to the coupling of this qubit. Okay? To this day, we cannot make measurements like that with optical photons, right? So the point is, you can now use this as a tool, and we will later in this talk. This allows us to measure the occupation of each of our lattice sites, okay, just by having one of these objects on each site, right? It's that standard at this point, okay? So, suppose you have 2 of these lattice sites and you want to couple them together. How do you do it? With a capacitor, okay? And so what you can start to see is the power of this kind of an approach is that you literally just lithographically lay down this quantum manybody system that you want to make, or the quantum computer that you want to do it for. Now, in the interest of full disclosure, the challenge, I would say the biggest challenge with this system, is that when you fab these transmon qubits, it's very hard to make them identical. Okay? I think the state of the art right now is either in Oscar's group or at IBM. And they get about 50 megahertz of disorder, qubit to qubit. The number I quoted the other day was a little bit lower than the reality. But the basic point is now you can actually tune up the individual lattice sites by adding squid loops to these things. We don't need to worry too much about that. But then the challenge is to actually make all your lattice sites identical, or if you're making a quantum computer, to make all your qubits identical. But other than that, this is really a beautiful ideal platform. And so one can, depending on the capacitance you choose, have a tunneling energy of 10 megahertz. And you can see this would be deep in the Montague if this were covalent. It would be a little deep in the Montague here as well. So the important numbers to keep in mind here are the interaction energy of about 300 megahertz, a tunneling energy of 10 megahertz, but you can make that bigger or smaller if you want to, just by changing the capacitance. Yes?
What was the noise level that you said? I think it was bigger than J.
But the point is you can correct it.
Or like this.
So we correct it in situ with a fluxer.
weird that I can think of capacitance as tunneling because it doesn't allow Cooper pair to physically move.
So the point is, the excitations of the transponds are not Cooper pairs.
Some like flux.
It's literally microwave photons, right? There's a regime in which it's Cooper pairs tunneling, but that's not the regime where we typically operate them, because those qubits end up very sensitive to charge noise, and they end up not being very good for.
So if I think about impedance of a capacitor, it is frequency dependent. So can I still model this as simple tunneling and not worry about this frequency dependence?
Yes. So okay. So this is a rather subtle question for experts, but the basic picture. This is the reason I cleaned the other side of this board. Who wants to see me just tip this thing over?
Yeah.
Just Norm. Okay, Norm and Eugene. So the basic point is this. And this is a sort of a general trick in analyzing all of these circuits, be they the topological circuits we make at room temperature, or what have you. If I have these two, right, and I couple them with a capacitor, which is sufficiently, these capacitors are sufficiently weak, the picture you should have in mind is that this thing only supports photons near its resonant frequency. Okay? So, as long as this capacitance is small enough that, I have all these resonators that each have a resonant frequency here, and this is 0. As long as the couplings here don't bring me a substantial fraction of the way towards 0, then it's totally fine to treat this as a frequency-independent coupling of 1 over I omega, where omega is omega resonance times C. Okay? Now, it turns out that in the topological circuits, sometimes we actually make this capacitor so huge that it dominates over that capacitor, and you essentially have this model. And then it doesn't map nicely onto a tight binding model, right? And when you calculate the whole thing, it turns out you have effective long-range hoppings. But at lowest order, making this frequency independent corresponds to the tight binding. Okay, so essential numbers to think about here. And incidentally, if you wanted to change the sign of your tunneling, what would you do? You can answer if you want.
Change your capacitors.
Do capacitors have a direction?
The others.
So what you could do, yes, you could, instead of coupling your capacitor from here to here, you could couple from here to there, right? The other thing you could do is replace the capacitor with an inductor, right? To change the sign of the tunnel. Because instead of 1 over I omega C, it's now I omega L. And as many of you may be aware, 1 over I is actually negative I. We can go back and prove that too. Okay, I just want to make sure you're all awake. Let's see if we can get to the science. But I think the important things to take away about this platform, particularly for those of you who are more theoretically inclined, is these numbers. Okay? The J we can make whatever we want. We can make it so huge that, as Eugene asked, you can't even think of it as a particular number. It becomes frequency dependent and things are a mess. Or you can make it so small it's 0. The two that are most important are U and T1. Okay? The statement is the photons live for about 40 microseconds up to a couple hundred microseconds, depending on how you fab these qubits. And their interaction energy is typically about 300 megahertz. So you can multiply these together, and that tells you qualitatively kind of how many collisions you get between photons before they leave the system. Okay? Probably you want to add an additional factor of 2 pi, but let's not even do that. That says we can get about 12,000 collisions within the lifetime of the photons. Okay? This is a phenomenal number, and in fact, it's as good as what one gets with cold atoms and lattices. Right there, one imagines a lifetime of a few seconds. Maybe we go to a cryogenic limit and can do better. But I think a few seconds is pretty typical. and interaction energies of a few kilohertz give very, very similar numbers. So this disorder thing is a challenge, right? But particularly if you want many-body localized physics, quantum circuits are the way to go, man. But in any case, these are very, very coherent systems. And so at present, this story that photonic systems are more open, right, and are good for open system physics or something, is not, I think, really a true statement necessarily. Now, I'll show you how to do some open system stuff, which is really beautiful. But the challenges are more with things like, it's harder to tune system parameters here. So driving these quantum phase transitions by tuning the Hamiltonian is less convenient, right? Or each qubit has to be fabricated, so making a big lattice like one does with cold atoms is a little bit challenging. But it's not really about open systems versus closed systems anymore in this regime. And you can see this U times T1 also tells you approximately how many gates you can implement in a quantum computer. So this platform was generated for quantum computing. And basically, Dave and I sat down, multiplied those two numbers together, realized that's what you need in a lattice, and you're like, geez, we should really make a Hilbert regime lattice. This kind of system. Okay, so that last slide was one I didn't finish, so I think we should skip it. So again, there are a number of very beautiful results from Andrew Howe's group. This is essentially a Doublewell system showing a transition from delocalized physics to localized physics as the number of particles in the system drops. So essentially at high particle numbers you kind of have a fluid, at low particle numbers you have a solid. Here's a chain of many, many qubits showing some disorder physics in a strongly interacting regime. The reason they study disorder physics is because generically if you make a chain of 70 qubits, what you're going to be studying is disorder physics. But that's not a criticism, right? In some sense, it's a very coherent system. It's very interesting science. And the next challenge here is how to really reduce the disorder there. People have started to study strongly correlated physics of pairs of particles in this kind of a system. So this is an experiment from Irfan Siddiqui's group, where they made a three-site chain with nearest neighbor hopping around a ring, and demonstrated the way they generated that hopping was by just putting all 3 qubits in one cavity. And so the neat thing about doing that is now you can also use that cavity to take entropy out of your system. Okay, remember we said we need some kind of a cold reservoir. Well, an empty cavity makes a very nice cold reservoir. And so they demonstrated some kind of early optical pumping into correlated states. And this is, I think as of a year or two ago, one of the newest chips from Google, where they were actually able to demonstrate some of this stuff with the distribution of 2-particle eigenstates that Norm was talking about relating to ETH and many-body localization. Yes?
So maybe you said it, I missed it. So do we have to worry about temperature, or is this a system that doesn't know about the temperature of the surrounding solid?
So this is a very interesting thing. I would say that fundamentally, one does need to worry about temperature at some level. So what's the challenge? The challenge is, so these are 4.5 gigahertz kind of transitions, and typically in a dill fridge, the fridge base temperature is like 20 millikelvin.
That's comfortable.
What?
Comfortable.
Well, it's like a factor of 10 or 20, right? So an e to the minus 20 is 0, right? For all intents and purposes. So, but the challenge is this. That's the temperature of the base of the refrigerator. Getting the qubits to really be at that temperature has remained a challenge. And people are doing better. Basically what they've been finding is that if any component in your measurement chain isn't well thermalized, if it has a piece in it that's not metal, like if you put a resistor in there that's got some some powder that doesn't thermalize well, which I guess was the big thing in March meeting last year, then you end up at 80 millikelvin instead of 20 millikelvin. And as soon as that happens, your occupation of these cavities in thermal equilibrium is like 0.1, right? And so typically what people do to get around that is a technique pioneered by Sir Charoche, which is before you do your experiments, you start by basically measuring the qubits, and if they're excited, driving the pi pulse to take the excitation. Right? So I would say it's not a fundamental challenge, but it is a technical challenge which is still in the process of being resolved.
Okay, but let's say if one can reach such low temperatures, can we see things like Bose glass at all? That's the hallmark of disorder Josephson junctions.
So I guess there's a question, at some point you need to put particles into your system and ask them to thermalize into that state, right? So then you need to engineer a reservoir, right? And then, so I see, so you just want to say, you just want to dump particles in and watch life. Yeah, so then you can certainly do that. And then, but then the question is, how long can you wait, right? How many decades do you have? Yes?
But actually, if you go back to the previous slide, I have a question. There is something I'm missing.
On this slide?
Not the one which was not perfect.
This one?
Yeah. If you say you dump, I don't know, 100 photons there, it means you've taken care of the chemical potential. And then with an attraction like this, why don't they clump all on the same side?
Well, okay, so this is a great question. How are we doing time-wise? We're doing okay, great. So why don't they clump all on the same side? Well, cold atoms can do that because as they start to clump, you get, 2 and 3 body loss. So the high energy particles can leave, right? And the thing can actually release that excess energy, right? If you don't have anything to release your excess energy into, then the particles look at planets in the solar system. They're just attractive, but as long as it's purely coherent dynamics, nothing can happen.
No, so you're saying that the question of being able to thermalize is absolutely crucial.
Absolutely crucial.
And what you see here is completely out of equilibrium.
Exactly.
Situation.
It's
It would perhaps not be the case with positivity as bad.
well, it turns out, I would argue it's exactly the same case with positivity. And this is where this story is kind of going. Imagine that I have a single qubit, just one, okay? And what I want to do is prepare it in the excited state, but have it always be in the excited state, in spite of the fact that it decays occasionally. Is there a drive that I can apply to a single qubit, right? So here's our qubit, ready? That's our marker grade there. So here's our qubit. It's got a ground state and it's got an excited state, right? So this is 0 photons and this is 1 photon. So what I want to do is prepare this qubit always in this excited state. How do I do it? Is there a laser I can apply to this thing to do that? You might say, well sure, just apply a laser like this, right? So that then, if it's ever in the ground state, it gets pushed up to the excited state. But here's the problem. What do we know about a two-level system driven with a laser? You get Rabi oscillations, or as I used to like to call them, rabbi oscillations. It's missing a B note for that.
It's because bosons don't have a Fermi surface.
Exactly. But so the basic picture here is, if it's excited, this laser de-excites it, right? So you only actually ever prepare it half the time in the excited state, right? And so this looks like a special case. You could imagine saying, okay, well let's drive the pi pulse and then continuously measure what state it's in, okay? And if it's in the ground state, then apply another pi pulse. And that's fine, but if you don't want to have any feedback in your system, it's very hard to keep the thing stabilized in this excited state, okay? And this is sort of the fundamental challenge of these kinds of systems. Imagine you have a lattice like this, right? That was a good marker. It doesn't need to go to the blackboard in the sky. Okay, So how do I prepare this system in a mod insulating phase? Well, you might say, and this is what Thierry was arguing, and I think it's sort of, it's not sort of, it's actually extremely important to understand this. You cannot just drive this system continuously and expect it to go into a mod insulating phase. Okay? Because basically we have this extremely coherent dynamics going on, right? So you'll put particles in, you'll take particles out, they'll collide with each other, but it doesn't go to the many-body ground state. Similarly, you can't just dump a bunch of particles into the system and wait and expect it to go to the many-body ground state, right? Getting to this many-body ground state in a unitary, strongly interacting system is non-trivial. So that's the story that I want to tell you in our remaining time here. Okay? So the picture you should have in your mind now relates to a fluid. So let's go back to pouring water into a cup. Okay? When I pour water into a cup like this, you're like, well, the water had all this extra kinetic energy from falling from the cup into the bowl. Right? And yet, I have, if I pour it slowly, I get a nice smooth surface. So, and this is where our confusion about this story always comes from, at least for me. This says I should just be able to inject particles into my system and go to the ground state. So where did the kinetic energy of this water go? Pardon?
The glass.
Exactly, the water, you heated, either you heated up the water and it has some motion that you can't see on very short length scales, right? Or you heated up the glass where the thing made some sounds and the energy went into that. And so fundamentally this is bad, right? This is stabilized by internal damping. And so now we talk about, well, what do we really want? We want to study quantum many-body states. As soon as you have internal damping in your system, there's something that's continuously measuring the state, right? And this is not going to allow you to have much entanglement in the states that you make at the end of the day. So what we would like instead is some fantasy bowl here, where I pour water in, but that's the entropy leaving. That's not water leaving. You can tell it's entropy because it's red, which means we don't want it. Okay? And the other point is, it's just leaving there. So once I'm done cooling to the ground state, then I can plug up this entropy hole, and nothing's measuring the system anymore, and I can have pure quantum evolution of this many-body system. Yes?
Is that really the right way to say it? I mean, because if nothing's measuring here, in a sense you're creating an extremely entangled state. It's just that these thermal states, they're so entangled with so many degrees of freedom that you're not interested in, that you lose the coherence in the usefulness, in the interesting part you're interested in. So in a sense, the thermal states are super entangled. They're the most entangled states.
So
actually.
I think the question is, what are the degrees of freedom that we're talking about?
Yeah.
I agree with you.
Yeah.
So the point is this. If you think of this fluid as only being the low energy degrees of freedom that you can actually observe, right? And this molecular rotations and stuff, which is where all this kinetic energy is going, as being external degrees of freedom that aren't part of your system. And that's sort of what I have in mind. Then you say these rotational modes of the water molecules actually are making measurements of your system, right? And it's like information leaking out. So that's kind of what I had in mind. But I agree with you, if you just dump your water in and it's sloshing around, right? That's actually a very interesting regime to study, right? Before it goes into these rotational degrees of freedom. And that's sort of, I think, what Thierry was saying. You don't have to make the many-body ground state, particularly if you had disorder. You could just study the dynamics. The problem is, it's not totally clear to me what the signature is to measure there yet. And so what we're trying to make is simpler ordered states to start with, and then you need this magic object. But fundamentally, I do agree with the manual that you have to be very, very careful about what's the system and what's the bath. Okay? So, basically the picture I would like you to have in mind now is imagine I could make one lattice site that continuously populates itself with a single photon. Okay? If it's ever empty, it just automatically repopulates itself. Right? And this was this thing that we didn't know how to make over here. Right? But let's imagine we could make it, and then we could hook it up to this Bose-Hubbard lattice. Because I haven't told you how to make the Bose-Hubbard lattice, right? It's just transmon qubits coupled with capacitors. So what would happen here? Well, this thing starts out empty, it fills itself with a photon, then that photon hops into our system. Okay? This thing refills itself, and now this photon can't hop into the system because of the repulsion between the photons. Right? And this thing also can't hop back into this thermalizer object, again because of the repulsion between the photons. But shortly thereafter, this photon can hop over by one side, because it is in this Bose-Hubbard chain, and tunneling is allowed. Okay? And then we can tunnel back into the system. Okay? And then this thing will refill itself, and so on and so forth. Okay? So it turns out there are a whole bunch of proposals for how to do this. The earliest one is from Elliott Caput, and he proposes what he calls a ghost lattice for stabilizing a fractional quantum Hall state. So he was very prescient, in fact. He didn't even start with the Mond insulator because he was only interested in these fancy topological states. So we weren't aware of his work until later, actually, for that reason. But this kind of an approach works for basically unentangled states, like a Mond insulator. I guess they have some string order, if J is large enough. And strongly entangled states, like these topological fluids. So thereafter, there are some sort of model-independent proposals from folks like Jacopo, which are Carasoto, which are really beautiful and very instructive, and more physically motivated ones from folks like Jake Taylor and Mohammed Hafezi, talking about doing this with Josephson parametric amplifiers. Okay, so what I want to do is tell you about how to make this object. Okay, so this is the Bose-Hubbard circuit. And so, what I'm kind of showing you here is these are the qubits. These are our transmon qubits. These are the readout cavities that allow us to measure the occupancy of each lattice site. They're coupled together by these small capacitive gaps between them. Then what I'm showing at the end here is some special drives for one of the lattice sites that we use to achieve this dissipative stabilization. Okay? So in the interest of time, I'll skip these details, but I've told you how to make this bit. How do we make this magical object? So who knows how a laser works? Okay, so that's Manuel's trolling again. But it seems like most of you actually know how lasers work. A laser needs a third level, right? Why does a laser need a third level? Yeah?
You can never reach inversion.
That's right. So it's exactly this story that I told you over here, right? The point is, no amount of laser driving of a two-level system will put it in steady state, mostly in the excited state, right? Which is what you need to use this object to provide gain in your laser. Yes? So what you need to do is have a third state that decays really fast, okay? Excite your system directly to that third state, and then let it decay to this upper state quickly. And then it'll live there. And then when it eventually decays, it's just immediately re-excited. Yeah? So the point is, that's what we want to do with our transmon qubit. Okay? It can hold 0 photons, 1 photon, and 2 photons. And as I promised, we're pretending that the 2 photon state is more than twice the 1 photon state, because otherwise the picture's ugly. And nobody likes that. And we're going to call this 2 photon state our state that needs to rapidly decay. Okay? So the challenge is, how do we make the 2 photon state decay rapidly? Unfortunately, these transmons are pretty well behaved, which means that the 2 photon state basically only decays twice as fast as the 1 photon state. So how do we make it decay faster? Well, this is the beauty of quantum circuits. Literally, all I need to do is couple this transmon qubit up to a resonator, which is resonant with the 2-to-1 transition, but low Q. Right? So this is what we call dissipation engineering. I've added dissipation to my system, but it's only dissipation at this frequency. Okay? So basically I'm able to engineer the line widths of the individual transitions separately. Okay? So this is now a cool object, because now I can excite this thing with a microwave tone that goes from 0 photons to 2 photons, let it rapidly decay to 1 photon, and it's this magic object that I need, which you can think of as a thermal reservoir, kind of like a chemical potential that supplies particles. Yes?
That's now a very naive idea, but why you could not just use a LC circuit like a not a qubit, like a real harmonic oscillator, and fill it up, and that's then like your bar.
Well, but the point is that thing's equally happy to take particles as it is to give them back. And remember, the key point here was that once a photon has gone into the chain, it can't go back into the reservoir. Yes? Because if it could go back, we wouldn't be taking entropy out of the system and going towards this manybody ground state. Does that kind of make sense? You need to break reversibility. So here's a question for you. Where is the entropy going? It's going into this lossy cavity. Right? Every time I put one photon into my system from here, there was another photon that decayed into this bag. So this relates back to Eugene's question now. Because if this cavity isn't at 0 temperature, right, it can actually put photons back into the system. And so now, you actually have a direct thermalization, intentionally, with a reservoir which is at the temperature of the dilution refrigerator, but not at the chemical potential of the dilution refrigerator. Right? The chemical potential of this reservoir is the energy of the 0 to 1 transition, more or less. Okay? So it's narrowband, it's not quite the same as a chemical potential, but, and Andrew Houghton is trying to make a real chemical potential, refers to this as the chemical potential light, or the splenda of chemical potentials, if you prefer. Which is to say he thinks it's disgusting, but whatever. It works well. All right, so I want to say this is not an idea that fundamentally should be new to all of you, because how do we take entropy out of a cold atom system? Well, one particle goes into the system at lower energy, and the other leaves through the edge of the trap, and the entropy leaves through these particles that leave. Right? And so this is fundamentally the same story that allowed the creation of Bose-Einstein condensates. And it relates back to Eugene's talk from the other day. How does one get a phonon laser? Well, one of these phonon polaritons goes to the lower band, the other goes to this upper branch. And if you shorten the lifetime of the upper branch, that destroys the reversibility of this process. Okay, so how does this work experimentally? In the interest of time, just believe me that it does. What we can see when we take this chain, this is an 8-site Bose-Hubbard chain. We measure the occupancy of each of the 8 sites, I guess this is 7 of them, as a function of the time since we turned the system on. And you can see the reflection of some filling front, and then the system fills up to 1 particle per site. And you can also remove 1 particle from the system and watch how that hole moves around, and do the same experiment with the stabilization on at this end, and now you see a random walk of the hole across the system that gets eaten when it gets to the other side. And so, anyway, I guess what I would say is that fundamentally this is kind of a new approach to stabilizing many-body states in synthetic materials, which is, I would say, orthogonal to, but similarly powerful to, adiabatic preparation of many-body states. And the hope moving forward is that groups realizing long-range interactions between microwave photons can use this to see double staircase kinds of phases. We're hoping to use it to see topologically ordered many-body states of light. I think there are all kinds of really nice opportunities there. So I think with that,
I'm not sure I really understood why why you couldn't achieve the same effect by just picking one qubit and then doing the routine where you're one transmon and doing the routine where you measure to see what state it's in and then
good. This is exactly the same process as that. The point is that because you haven't had to do the classical feedback, you can do it faster and with a lower error rate.
Okay.
And the other point is, right now we just have one of these thermalizing objects at one end of the system. But that only works if the whole defects are mobile, right? Generically, you know, like in a fractional quantum Hall state, the whole defects are less mobile. So you'd like to have these objects everywhere. And do you really want to be measuring, you know, every fourth site? No, you want to have some kind of autonomous object that allows you to stabilize your many-body states. And you can also imagine now engineering things where there are multiple energy bands where you can inject particles, right? And multiple energy bands where you evaporate particles. So fundamentally, how the individual objects work, I agree, is 6 of one, half a dozen of the other, but it's technically nicer.
So I don't know the full circuit toolbox, but can you utilize some of also the spin?
So we've been thinking a little bit about this. There are these sort of more sophisticated qubits that one can generate called fluxonium qubits, where in addition to having a Josephson junction to act as a nonlinear inductor, you also shunt the thing with a regular inductor. And then, instead of having a potential that basically looks like a sine wave, and making it deep enough that there's no tunneling between wells, this is a pretty technical statement, such that all of the physics occurs in one well and the inharmonicity is all we care about. You can make this potential shallower, use the inductor to give you an overall harmonic trap. This is all in one transmon qubit. This is how a transmon qubit works internally. And now you have a potential that kind of looks like this. And you can tune these two to be at the same energy. And you can call this spin up and that spin down. And in fact, folks have seen T1s that are 100 times longer for the spin degree of freedom. Right? So that sounds great for doing many-body physics, right? The only problem is that T2 is 100 times shorter than it was before. So anyway, ultimately, I think that once that ingredient is fixed, this will be an amazing system for spin physics. Long answer to a short question. Yes?
I have a question about tunability. So, for instance, if you want to study this like multi-insulator to superfluid transition like stuff,
Yeah.
and because you can't change your like capacitor to inductor, or like you can't change your capacitors like capacitance during your experiment, how do you study that kind of physics? So can you create like a tunable Josephson?
Yes. So that object, would you believe it, is called a tunable coupler because it tunes the coupling between transmons. The problem, and it's basically made of another transmon, right? So this circuit from Google is identical to ours, except that it doesn't have the dissipative drive, and it does have tunable couplers between all of the sites. So it substantially increases your complexity to do this, but it's certainly achievable. So I would like to make a broader, so you can just directly go from large J to small j.
So you said they don't have a dissipative drive. I thought it was for like entropy.
Yeah, so what I'm saying is they don't have this dissipative stabilization stuff that I told you about, but their circuit is 8 lattice sites with tunable couplers between them. So they can do the whole thing. But I would like to make a broader statement about many-body physics that I think is sort of important. My view is that this platform is not trying to be cold atoms, right? Part of what makes this science so fun and interesting is that the different platforms have different strengths. And, you know, the point at some level is to find new ways to stabilize many-body states and new tools to explore the many-body states that are not the same. I mean, if you want to do the superfluid to Mott insulator transition, quantum gas microscopes have that down pat. I mean, it's just a beautiful, beautiful system for doing that, right? So we're exploring different, and I think similarly interesting, but very different science. And so that's why we didn't try to go that route. Yes, and we have a flat bottom trap, or a random potential trap. You pick your poison, right? Yes?
So the many-body state you have stabilized is a Mott insulator state, which I consider is like a product of single particle orbitals, basically. And would you be able to stabilize a state, like superfluid state, that has coherence among cells?
So I skipped, so two things. One, we have a very small jet. So the string order that should be present in the Mott insulator from the Doublewell hole effects is hard to measure. But fundamentally, this state does have some coherences between the lattices. So that's statement one. Statement two is that this approach should work generically for any incompressible phase of matter. What do I mean by incompressible? I mean, you put particles in, and there's some range of energies that you want to put them in at. And then once the system is full, once you've made the many-body state, putting in the next particle requires a higher energy, right? So you don't want to have a whole spectrum of energies that you can put excitations in at before you fill up. And then you need to have a gap once you're full. So a superfluid doesn't actually satisfy either of those requirements. As you're filling it, it has a whole bunch of low energy degrees of freedom. And there's really not much of a sense of full, right, where it suddenly jumps. So that means a superfluid is bad. But you can imagine making a fractional quantum Hall state where you don't have one particle per site, right? It's some smaller filling, but once you fill up to this fractional quantum Hall state, putting in another particle requires a whole bunch more energy, right? So this is not something that works for all states per se, but it works for a lot. And indeed, we're now implementing this for our optical photons, or figuring out exactly how to do it. And the claim is a special type of incoherent repumped Raman scattering behaves just like this object, right? So you can directly stabilize fractional quantum Hall states with this kind of approach. Yeah?
For this question, so for a fractional quantum Hall impact, when you pump it, you pump like incoherently, and do you expect the system itself to stabilize it to the fractional quantum?
So I would say the way I think about it is you should think about having one of these stabilizers at all points in space. So it's trying to put low energy particles into your system, okay? Or equivalently, it's trying to pump out pairs of quasi-holes. You're making a new equals 1/2 logless, okay? And so, you know, Jacopo Carasoto calls this incoherent pumping. I think that's a sort of slightly confusing way of describing it, because there are lots of ways to pump something incoherently, and most of them don't do what you want, unfortunately. But, you know, there you better make sure that your quasi-holes don't move apart, because then you can't, you know, you can't refill a fraction of a quasi-hole, or a fraction of a photon with a photon. But fundamentally, this kind of an approach, I think, does kind of work. And Jacopo has numbers indicating that.
So you try or able to make molecules of these? Dimers and trimers?
So, I see. So you're saying make something that looks a little bit more like an interacting SSH chain or something, and see. So we've thought about that. That's one of the next things we're trying to do. Again, the challenge a little bit is getting really good control of the disorder, because I don't know how excited you'd be about a dimer chain that's 8 sites long. You might want 30 or 40 sites. But it's an interesting comment, right? Because we can control the energy, so you could make a dimerized system either by controlling the tunneling or by controlling the on-site energy. Yeah, we can certainly do that.
Other questions? Then, let's thank John for a beautiful presentation.